All right, so this time we're going to look at a slightly different situation. Last time we used binomial distribution and we were looking at a situation where we were hiring a group of people from a population where a certain percent was considered success and a certain percent was considered a failure. And we were concerned with how many successes we got in our sample. Now this fits the binomial distribution because we have a constant probability for each trial, a fixed number of trials, and we care about the number of successes. So we're hiring 10 people, that's 10 trials. If 60% of the population is female, then we have a probability on each hire of 60% success being female, and we care about the number of successes we get within our trials or our samples. Let's change that a little bit. Let's say that this time we're hiring 10 people, but we're looking instead at the applications that we've received. We've received 20 applications and 12 of them are female. That's 60%. What's the probability that 4 of our hires are going to be female? You know, the difference between this and the previous situation is every hire that we make, every time we hire one of these 20 applicants, the probability that the next one will be female is changed because we've changed the population. One could argue that we've changed the population here too, but if we're talking about a population of 10,000 people, we're not changing it very much by pulling one person from it, turning them from a member of the population into a member of our sample. Here, where we've only got 20 applicants and we're going to be hiring 10 of them, we're going to be drastically changing this population by the time we're done. So we need different math to make predictions in this particular situation. The characteristics of this situation are that we're starting with a finite population. That's different from here. That the population is made up of successes and failures. We're going to pick a fixed number from the population, and we care how many of them are going to be successes and also how many are going to be failures. And again, I feel I need to disclaim this every time. Success is not good, failure is not bad. It just means fitting the description that we're looking at and not fitting the description. So we're pulling from a finite population. This is really the key because every time we draw somebody from the population is going to change the probability of the next one. The population is made up of successes and failures. We're pulling a fixed size sample, and we care about the number of successes we have in our sample. All right, so this part's the same, where we're pulling a fixed sample size. This part's the same as, the same as when we're doing binary distribution or binomial distribution. Binomial distribution, sorry. And we care about the number of successes in the sample. That's also the same. The difference here is that the math's going to be a little bit uglier. It's not going to be really that bad. It's going to be ugly to look at, but it's not going to be difficult to do. So don't be frustrated by this up front. We're going to be using 4 variables here. Capitals are for the population. So the number of people in the population is N. The number of successes in the population is K. And then lowercase for the sample. Lowercase n is how many we're choosing in our sample. Lowercase k is how many successes we're talking about in the sample. So if we go back up to the top here, for this particular situation, our population is 20, so that's big N. There are 12 successes in the population, that's big K. We're choosing a sample of 10, so that's little n, and we want to know the probability that there are 4 successes in the sample, so that's little k. And you're going to want to have this formula written down somewhere. Eventually, you're going to want it in your head. It is not as ugly as it looks. If we go back to when we were talking about probability and counting methods and stuff, you remember permutations and combinations, and I told you they were going to come back to bite you. This is the combination. It's really simple, though. If you think about the fact that it's capital and lowercase, it's always going to be population, C, sample. So we're starting with successes in the population, C, successes in the sample. N minus K is just the number in the population minus the number of successes. So just think of that as failures. Failures in the population, C, failures in the sample. and then the whole size of the population, C, the whole size of the sample. Okay, very simple. And the formula for the mean is just little n times big K over big N. And if you're actually thinking, you really shouldn't need a formula for that anyway. If we get 20 applicants and 12 are female, and we choose 10 from that, you would expect the same percentage. So you would expect 6 females, and that's what you get if you would do this little formula here. Okay, now let's run through one of these real quick, or a couple of them real quick, just because I don't want to leave you hanging. So suppose that we have, why did I even put that on there? Okay, we have 10 people apply for a job and 6 are female. Now let's not do that one. That's a contradiction, and it will just confuse you. So suppose we have 100 people applying for the job. 60 of them are female. Same percentages we've been dealing with all through this example. We're going to hire 10. What's the probability that 4 of them are female? So let's get our numbers here. The number in our population is 100. The number of successes in the population is 60. The number in our sample is 10. And little k, the number we want to find out about, what's the probability that the number of successes in our sample will be 4. So the probability that it's going to be 4 is just going to be successes, C successes, right? So another way to think of this is we have 60 successes to choose from. We're going to choose 4. How many ways can we choose 4 from 60? That's what the C notation meant. Okay, how many guys are there in the population? 100 minus 60 will be 40. So we have 40 guys to choose from. How many ways can we choose, or how many guys are we going to put in our sample here? If we got 10 in our sample and 4 of them are female, that means that the other 6 are going to be guys. And we're going to divide that by the size of our sample, 100 C, the size of our population, C, the size of the sample. Okay, so successes, population sample, failures, population sample, whole population sample. And the bad news is the calculator doesn't do this for us. So we're going to have to do this one by hand every time. It's a little tedious, but it's not impossible. 60. Remember, C is under math over to probability there. 60C, 4 times 40 C, 6 divided by 100 C, 10. And we do not have to put any parentheses or anything in like that. We're lucky that we don't, because that would just make it uglier. But that'll give us what we want, which is 0.108, or about 10.8% of the time we would end up with exactly 4 females in our sample. If you remember back to the previous example in the binomial, we actually ended up with about 11.4% there, I believe. So it's a little bit different, but not by too much. We'll get more into this next time.